Okay, so this is kind of gonna feel like maybe like a part two of the previous video, but actually I'm gonna give this one its own title, uh, tautologies, right? So I just want to show you even more tautologies, um, because again, you never know when you're gonna need a tautology. You never know when you're gonna think, this statement doesn't seem that easy to prove, but I can prove this other statement, right? Or just like I said, just to know, okay, no matter what, this statement that I'm saying is always true, right? So we'll see. We'll see how it goes, right? So let's see some more tautologies, right? Because I already introduced we already introduced the best tautologies that we're gonna use. But hey, some of these ones are pretty good, and some of these ones are kind of like pretty obvious, right? So I'm not so for example, for these ones right here, I'm not even gonna make a truth table, right? So for example, the statement P and Q is equivalent to the statement Q and P. You know, yeah, I'm not even gonna make a table for that. Uh, if you don't know how to make a table for that, well, let me know. I'll do it, I guess. But well, I mean, the only thing interesting about this one is kind of like saying, people take for granted that A times B equals B times A, but I think in one of the videos we show where like maybe not multiplication but something else. It was like this something that was not equal to that something this, right? So again, if there's any value to this, it's just to say, it's kind of like it's reflexive, right? A times B equals B times A. It's commutative, whatever. Another one that I'm not gonna do a truth table for because I think it's just, come on, just wasting time, is this other statement: P or Q is equivalent to the statement Q or P. So again, I said time. This one I refer to it as times, right? This one you can think. A lot of people make a connection between the word and times, and then they make the connection with the word or with summation. If you haven't heard that before, don't worry. We'll get to that someday. But again, in the same way that A times B equals B times A, this kind of like saying A plus B equals B plus A, right? Another one that you probably won't think much of, but again, just as a math major, I find this interesting. The statement: if P and Q and R is equivalent to P and Q and R. So again, why do I say that as a mathematician? I find it interesting. Well, because it kind of, again, if you think of this as multiplication and this one as addition, this kind of feels like that the multiplication, quote unquote multiplication, is associative. A times B times C equals A times B times C. Again, when it comes to proving, yeah, you want your numbers or your whatevers, your logic, to be associative. And again, similar, this one right here, P or Q or R is equivalent to P or Q or R, right? I mean, again, if you translate any of these into English, and then they sound like yeah, duh. Like if someone tells you, again with that whole Price is Right thing, that's not even a realistic example. Someone tells you, oh, you can pick an object that's blue and a car, and then someone say that the contestant says, oh, so you tell me I can pick something that's a car and blue? That's like the significance of that. Yeah, picking something that's blue and a car is the same thing as picking something that's a car and blue. And then, same thing with the or, right? And then same thing with the associative, right? If something that's a car and blue and, I don't know, made before 1999, whatever, right? Then that's same thing as car and blue and made before 1999. Again, now that I put in sentence, maybe it doesn't look that obvious, but you can do a truth table if you're getting shaken up. Okay, so I'm not, like I said, I'm not even gonna do a truth table for those. Let me see what I can do. What's interesting to make a truth table for? there's a lot of things that I have in mind, but let's look at this one, right? So I already said before this one, right, that the statement basically the statement P or not P, right? So this statement P or not P is a tautology, right? Meaning this statement is always true. Well, the statement P and not P is always false. And I did define this in one of the videos before. A statement that's always false is a contradiction. So the statement P and not P is a contradiction. So another way to put that is this following way, right? The statement, yeah, okay, right here. I'll put it right here. So the statement P and not P is equivalent, meaning if and only if, to the statement C, where C is a contradiction. Now, I think even in the prologue videos, if you watch the prologue videos, I did use the word contradiction, even though I didn't really explain what it was. But like a contradiction is saying, you know, something. This is basically, it doesn't get any better than this. A contradiction is when you're saying that a statement is true and its negation is true. I mean, when you say that the negation of a statement, if you say not P, the statement not P is true, then you're basically saying that the statement P itself is false. You know? So a contradiction is when you're saying that one statement is both true and false. You know? I think when I said contradiction, I said something like, we did a proof where like we assume something, and by assuming that, we ended up with a sentence that read 1 is less than 0. Now, what was that a contradiction? Because we know that in reality, 1 is greater than 0. The negation for the statement 1 is greater than 0 will be equivalent to 1 is either equal to 0 or it's less than 0. So, you know, if you arrive at 1 is less than 0, then you're saying the statement 1 is less than 0 is true, while at the same time we know in reality that the statement 1 greater than 0 is also true. So you know, how can you spot a contradiction? The only way to spot a contradiction is basically this. Anytime you find yourself saying, oh, the sky is blue and also the sky is not blue, you know, this car, the car over there is red, but also that car over there, that same car over there is not red, you know. It like, again, in math you will find statements that sound so unbelievable but they don't contradict each other. So, you know, the more you learn about math, the more you might even doubt reality. Oh wow, can't believe I said that. But what I'm saying is that, like, you might hear something about like, oh, a set is both open and closed, and your brain might think, well, that sounds like a contradiction. It's not. That's gonna come that way in the future. But the statement the set A is open and the statement the set A is closed, surprisingly, that's not a contradiction. The only way that's what I'm trying to nail down right here. The only way to spot a contradiction in mathematics is when you, clear as day, you end up you end up in your argument saying the statement P is true and also the statement not P is true, whatever that P statement might be. That's the only way to spot a contradiction. So let me do a truth table right here. What I mean by this, right? So by the way, when I say this is equivalent to C, where C is a contradiction, I'm just saying that when I make my truth table, the only value for C is false all the way through. In the same way that for a tautology is only a tautology if the only value is true always, right? So then a contradiction is a contradiction if it's false always. Well, actually, I don't need to make that a big table, right? All I need is P, and then negation of P. So then P and not P. And then what I was saying about the word C is the letter C, the statement C, is that before I even fill these ones in, because I'm calling this a contradiction, this is always false. Okay, so I filled that up right away as the first thing I filled up. Now let's fill up the other things, right? Well, I'm only dealing with the letter P, so this is either true or false. If this is true or false, then this is false, true. Okay, but now we're dealing with the statement this and that, this and that. So true and false makes the statement false, and then false true makes the statement false. And you see, right? They match. So basically, yeah, if I make a truth table for this, then that's a tautology, right? I mean, I'll do it even though I really don't have to. P and now P, if and only if C. Well, yeah, right? If this is false, then the if and only if statement is true. This is false and this is false, then if and only is true. Whatever. Alright? So, yeah, it's so funny. Well, I mean, I do find it funny how this P or not P is a tautology, but then P and not P turns out to be the complete opposite. It turns out to be contradiction always, right? This one looks kind of interesting, so I'll show you this tautology. Only because I'm bringing up this letter C, right? Suppose that you have the statement I'm gonna put it in quotation marks. If not P implies a contradiction, if and only if the statement P. So this one also kind of ties up to proof by contradiction, because what did I say before? In a proof by contradiction, you prove that the negation of if P then Q is false. Therefore, it must mean that the statement itself is always true, right? Well, that's kind of what this statement is saying right here. That if the negation of P leads to a contradiction, that can only happen if P, right? So let's do a little table. So this is not a complicated table because again, we really only have one letter, P. Why do I say that we only have one letter? Because the other letter we have is not P, and then the other letter we have is just C, which again always false because we're assuming it's a contradiction. So if this is true or false, then it's going to be false and true. And what are we actually looking at? So we're looking at if and only if this, which is C. Oh, okay. We're looking at not P implies a contradiction, right? So you know, they're right next to each other, right? So if this is false, well, this actually becomes true because you start with something false. If this is true and this is false, then this is false. And I guess that's really it, because you know, true false. So this statement not P implies C is equivalent to just P. Again, this is kind of like another, you know, reinforcement of why proof by contradiction works. So that one was interesting, but I do have a limited time, right? I do have a limited time because I don't want this to be a gigantic video. So I kind of want to drop a bunch of them on you. And I don't know. Hey, this is supposed to be kind of interactive, right? So maybe I'll let you guys deal with it, prove it on your own, right? So let me give you a list of a bunch of tautologies I want to give you. I know there's one that I definitely want to do. There's one that I definitely want to do, and so, all right. I just don't know how much time I got, right? So let me give you this. Let me give you a couple silly ones. I mean, I don't know if you want to really call them silly, right? But just like this one, right? Just kind of like this one. So the statement, you know, so this, I'm saying that these are tautologies, but you should definitely confirm them by doing the truth table, right? So here's another tautology. The statement P and if P then Q. So if P is true and the statement if P then Q is true, then that should mean that Q is true. Right? So this is a tautology. Now notice that this one doesn't have an if and only if. This is just, you know, just claiming. If the statement if P then Q is true, but also the statement P is true, then it better be true that Q is also true. That's what this means in plain English, right? So I mean, I'm pretty sure you can do that one on your own, right? All right, so let me give you this one again. Maybe it kind of sounds silly, right? So, but I think this is logical, right? And again, you can double check if it's logical. Suppose you have the statement: if I tell you this or that, right? I tell you P or Q, and also I tell you, well, it's definitely not P, right? If I say P or Q, and I tell you, well, it's not P, then you can just say it's Q, right? Does that sound like it makes sense? Well, again, you can check if it makes sense with truth tables, right? But yeah, right? If I say P or Q and it's not P, then it better be Q, right? Well, let's see. What else can I give you? I guess a very, very obvious one, right? If I say, that statement P and Q is true, then P is true, right? This would also work basically. So this would also work if it said if P and Q, then of course Q, right? Right. If I say I have, you can come up with your own sentences, right? If you have an object that's blue and a car, then it's definitely blue. If you have an object that's blue in a car, then it's definitely a car. Whatever, right? Again, I'm telling you that these are all tautologies, so this is a statement that you can't say is true all the time. Now, what about this one? Suppose that I say the statement P implies Q and not Q. So as I'm saying, if P then Q and not Q, then not P. Does that sound like it should make sense? Well, the only reason why I can give you like a quick yeah, it should make sense is because it kind of sounds like the contrapositive, right? If I'm saying P and Q is true, and I'm also telling you that not Q is true, then not P, right? If you say it in English, it kind of sounds like the contrapositive, right? And we already said that the contrapositive is definitely also a tautology. Well, if P and Q is P implies Q if and only if not Q implies not P. So these ones, let me give you more tautologies, but these ones are kind of more complicated, right? And again, I'm just because of time, I'm gonna make up your own sentences for what P, Q, and R are gonna be. So for example, I'm just gonna drop this on you right now. The statement P and Q or R is equivalent to the statement P and Q or P and R. So again, you make up your own sentences, just so that we don't run out of time. But come up with some sentences and statements. I guess I should have said statements. Come up with some statements for P, Q, and R, and then tell me if they make sense, right? But I'm dropping that one on you. Let me drop another one on you. Well, kind of like the opposite. Now suppose it's P or Q and R, and I'm gonna say that this is logically equivalent to P or Q and P or R. So again, supposing that you have some statements of your own for P, for Q, and for R, do these two make sense that they are statements that are always true, right? This one's I think a big one, because this one basically revolves about everything that math has to do, right? When I say you get to A to B, Well, how do you get from A to B, right? Well, you say this implies that, this implies that, this implies that, this implies that. Therefore, this thing or ultimately implies the thing that's at the end, right? But my question is, does that actually make sense, right? I feel like I should almost prove this. If we have time, I'll prove it. But what I'm saying is this statement, right? That if, let's say, suppose that for now you only have two. If P implies Q, and if Q implies R, right, then P implies R, right? And again, this one's not if and only if. It just says if all this, then that, right? But it makes sense, right? If this implies that and that implies that, then you're saying this implies that, right? Well, just to put that as a generalization too, right? Look at this statement, right? I mean, if this is true statement, which it is because this is part of the list of tautologies I'm giving you, then suppose now it was a bigger list, like statement 1 implies statement 2, and statement 2 implies statement 3, and statement 3 implies statement 4, and suppose you have a big chain of this, right, until you get to the penultimate. Let's just say P n minus 1 implies Pn, the last one. So the penultimate implies the last one. If you have this whole chain of conclusions, this implies that, that implies that, and that implies that, and that implies that, and that implies that, then this is then you can say, well, all this implies that P1, your very first statement, does ultimately imply your last statement. Now, in order to prove this big one, in order to prove it perfectly or properly, we will need something that's called a proof by induction, which is going to be the very last video of this whole series that I'm doing about logic and proof and all that. So instead, again, you should prove this one, right? And I mean, if this one makes sense, then you can kind of imagine why this one should make sense, right? If this implies that and that implies that, then yeah, this ultimately implies that. That's what math is when someone says, well, if x equals this, then x equals that, right? Or something like that. That in between is this is what describing all the in between spaces and why it still makes logical sense. All right. I want to drop an extra one. This one's on me, by the way. So this one also reinforces proof by contradiction. So the statement P implies Q is equivalent to the statement P and not Q implies a contradiction. Right. So just the regular statement if P then Q is true if and only if the statement P and not Q implies a contradiction. So again, if you make a truth table, you'll see that this ends up being a tautology. So okay, finally, let's get to this one, right? Oh man, what's the last tautology I'm going to give you? And this one I'm actually going to prove, right? So it's just interesting. It might be useful in the future, but look at this thing, right? Again, if you can come up with this one by just trying to make up your own, right? But I guess I'm like telling you that it definitely is a legit tautology. So the statement is, suppose that P implies Q, and suppose that R implies S, and you know that either P or R is true, then what does that mean? So if P implies Q and R implies S, and P or R, the beginning parts if you know that at least one of them is true, then what is the conclusion? That either Q or S, right? If you know that this is true and this is true, and you know that at least one of these is true, then at least one of these two has to be true, right? So that sounds like it should make sense, right? But so why did I want to do this one? Is because it has 4 letters, P, Q, R, S. So P, I'm not gonna have enough space. Well, why am I not gonna have enough space? Because I'm gonna need basically 18 different cases, right? So, right, if it was 3 letters, we need 8 different cases. So then, if we're gonna have 4 letters, it's always double, right? I don't know if you remember. It's always double. So P, Q, R, S. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Damn, see? It's gonna be a big truth table. Now, I don't know if you noticed, right? But there's like a quick way of like filling the truth tables in though. So, right? I don't know if you kind of notice that the patterns that I've been doing so far. I mean, what was it? It was like true, false, but then it was okay, true, true, false, false. So you rewrite it again, right? And it was true, 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 and then false, 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 right? And again, you rewrite this again, right? So true, true, false, false, true, false, true, false. So can you guess where this is going? So the fact that I know that it's 4 means that I knew it was going to be 16, right? I mean, why? Because 2 to the power 4 is 16. You know, why was 3 letters 8? Because 2 to the power 3 is 8. Why was 2 letters only 4? Because 2 to the power 2 is 4, right? So basically, I can already did have this table, but what I was going to tell you is, if you notice, there's a trick. If you know that there's going to be 16 in total, right? Or whatever total you know it is, just cut it in half on the first one, and you know half of those have to be true. So the first 8, 1, 2, 3, 4, 5, 6, 7, 8 have to be true, and then the next ones are going to be, the next 8 are going to be false. Well, what about the next one, right? Well, it's kind of half, right? So now the first 4 are going to be true, the next 4 are going to be false. So then same thing again, the next true are going to be true, and then the next 4 are going to be false. And then again, it's like getting cut by half again. Now it's pairs of 2s, 2 truths, 2 false, 2 truths, 2 false. So again, 2 truths, 2 falses, 2 truths, 2 falses. And then this one's just alternating true, false, true, false, true, false, true, false. So we ended up with false, right? So then true, then false, then true, then false, then true, then false, then true, then false. And that's gonna be like a quick way of like filling in those gaps, right? Honestly, this is the only reason why I wanted to do this one in particular, just to show you that little trick of how to fill in truth tables quickly. I now that I showed you that, I kind of don't even want to show you the rest of the proof, but I guess I already put my foot in my mouth, right? What's the statement that we're proving? We're proving that if P implies Q, I believe it was, and R implies S, and P or R, right? The beginning parts, P or R. Then all this implies that it's either Q or S, right? So what am I need? I need a P. If P then Q. If P then Q, I'm gonna need this. I'm gonna need a if R then S. I'm gonna need a if P then P or R. P or R. And then I'm gonna do let's just say that this is A, B, and C. Then I'm gonna do an A and B and C. Then I'm gonna need a Q or S, and let's call this D. I don't know, that's A, B, C, D, E, right? And then the last one is gonna be basically E implies D, right? Well, I don't even have space. Before I do this, you know, if you don't want to stick around to watch this, make sure to leave a like, comment, subscribe, um, and let me know what you thought of this video, because it's basically over. But I'll just do this video anyways. I'll keep doing it because I'm a math major, and math majors, they just love pain, you know. It's fun. It's fun pain. That's what math majors are. If you choose to be a math major, you're gonna have a lot of accomplishments because you're gonna tackle hard problems, but they're hard problems, so you're gonna suffer through them. Okay. If P then Q. True. Yeah. True. I guess I'm gonna have to, yeah, true and false, right? So false. But then they're all gonna be true again because they all start with false. Okay, that one was easy. If R then S. Oh, this was gonna be complicated. Okay. True makes it true. True false makes it false. Okay, but then now we're starting with falses. So true. True, false. I guess it's just gonna be this the entire way. True, false, true, and then true, false, true. Okay, not too bad. P or R. Okay, so yeah, I gotta look at these two, P or R. So true. I think it's gonna be mostly true, right? True. I mean, it can only be false if they're both false. True. Okay, finally a false. Another false. True. False. And false. So yeah, well, okay. And then now I'm looking at the A and B and C, meaning this statement will only be true when all three of them are true. So true. One false, so it's false. True. One false, so it's false. And more than one false. False. True. False. True. False. Was there a pattern to this? I'm not sure that there was. I'm you know, it's funny because, like I said, I didn't make a mistake before, so I'm trying to like double check. Oh, hopefully I didn't make any mistakes yet. Q or S? Q or S? Wow. Q or S? So it's or though. It's or, so that should be fine. True. But this one's false. Q or S? False. Wait, am I doing this right? Yeah, no, I messed up already. So I saw true. This one's false. This one's true. See, this is what math is pain though, because one little mistake and you're gonna end up looking like you don't know nothing. False. True. False. True. So again, hopefully I didn't make any mistakes. I mean, it should only be false if they're both false, right? But it's hard to read this whole thing. But okay, whatever. Now I'm saying, so I'm saying that this whole thing, then that should be a tautology, right? So these all need to come out as true. True. It's this. This implies that. True. 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 It starts with a false, so it needs to be true. Starts with a false, so it needs to be true. Starts with a false, so it needs to be true. Starts with a false, needs to be true. True. Starts with a false. Starts with a false. Starts with a false. True. And then the others start with a false. Wow. So the fact that they all came out true, and I already knew from the beginning that it was tautology, means that I must have done it right. But yeah, right? So now because it had P, Q, R, and S, it got so complicated. Well, it's so big, right? I mean, it's a very complicated statement. Look, you needed this table, then that table, then that table. Then you need to do the AND for all three of them. Then you need to do the or that, you know. So it's not just the fact that it was four of them, but that this statement, this whole thing is just a convolution of a lot of things. But okay, I don't know. I'm satisfied. It ended up with all true table, so it's a tautology, right? So this is a statement that's always true. If this implies that and that implies that, and you know at least one of these is true, then either Q or it has to be true, right? So I'm just saying that's a thing that actually makes logical sense no matter what anyone tells you. You know, if someone thinks that you just made a wrong argument, no, this is a tautology. It's always right, no matter what P or Q or R or S. There could be whatever statements you want, but this will be a true statement always. All right. Well, if you made it this far, then hey, leave double a like or something, or more like I need to give you something, because I mean it was only more like 7 minutes later, but still, you know, I'm glad that you're a trooper, and you'll probably make it far as a math major if you became a math major. So, all right, so that's probably, I think that's the end of truth tables. Really, like I said, the entire list I gave you before of tautologies. You know, again, if you have that drive, that spirit of, you know, finding truth, not just having someone tell you what the truth is, but actually finding it, then you should double check that every single tautology I gave you actually is a tautology. You know, if you have the time for it, I suppose. But it's not about having the time for it. It's about having the want for it, right? The drive for it. So yeah, P and Q, if and only if P and not Q implies a contradiction, right? So if you do this one, if you decide to do this one, remember that when you do the truth table, the C needs to be false throughout, you know, because it's a contradiction. All right, yeah, I'll leave it there, and thank you for watching. Leave a like, all that. See you guys later.